Hello everyone. Today's video, or I guess this week's video, is going to be talking about the EDL Sim. Yes, I am aware it says re-entry, and the probes will not be re-entering any atmosphere, because it'll be a new atmosphere. But in the GitHub version of this code, it is EDL. This is just internal. As you can see, I have a few versions of them here. But so basically, this section is to categorize and simulate the EDL portion, or the entry, descent, and landing section of this mission. Of course, we'll have our probe plus aeroshell, and this will detach from our orbiter, and this entire section has to perform a burn, a retrograde burn, and that is to lower periapsis. And once we lower it enough, we will start to encounter much stronger air resistance in the atmosphere. And do that, it's kind of a compounding effect, because then our velocity is brought down, which means our orbit arc is shorter, which means we encounter more air. So we need to perform a burn to bring down our periapsis enough that we'll start to enter the atmosphere. And then that's when we hit the descent section. So that's where we get things like aerodynamic heating, you're creating plasma gas, and that is some of the biggest thermal stresses of, I would say the biggest thermal stress is just flat out of any part of the mission. And then you've got to slow down, of course, in the air. And for the MAGPIE, we use a drogue chute and then a main chute. Other have used either none or airbags, or sky crane right at the end to slow down, not just the parachutes. But we're going to use something different. Basically, we're going to use the probe here. So this is what an extended probe looks like. This is not what it'll look like coming down to the surface. But we've got a disc here, which is a honeycomb design, and this will impact a lot, or crush and take a lot of the kinetic energy out of the system. So with the EDL, we need to kind of initialize a few things. We need to start, what is our orbit, what is our, we're going to assume circular because it's easy, because it doesn't really matter, because for this we'll be in a circular orbit because of previous scripts that you've seen. That is the orbit calc. So let's talk a little bit about the code. We have quite a few inputs and mode selectors. Of course, we've got our time. This doesn't have super good guidance. That's a thing I want to implement later on as I work on more of the actual control systems. So that'll be integrated in a future system, but for now, we're not worrying about that. So these are just our write-outs, what we want our path to be. Debug. Plot controls, if you're rerunning this and you're changing things, it can be really annoying to close like 15 different plots. It's really annoying. So I have like save, or you can show, or just none. So you can do dust storm. So what Mars 2, the Soviet probe entered during a storm, and it just failed because it was a storm. So we can enable that. I'm not, because we have no real reason to. But yeah, so our circular orbit is at 250 kilometers up. And then our periapsis goal is 35 kilometers. That'll be plenty enough to bring us down. We start the entry interface truly at 125 kilometers. That's like when we start to do the actual more mathematical part of the simulation for aerodynamic heating and stuff like that. So staging. This is very important in the simulator. So in this, we are not calculating this total mass and it's coming down to the surface. We have a modular mass. So that means that this calculation does things in stages. So for example, we do the retrograde burn to initialize the entry interface. We're going to use fuel for that. That's just how it is. And we'll use all of our fuel. The reason we'll use all of our fuel is it's only to our benefit. Terminal velocity is the thing, and we will hit that. So adding more energy into our speed doesn't really hurt us in this case. It just increases the thermodynamic loading of the aeroshell. So yeah, we'll assume that we deplete all of the fuel. And because we have the fourth thruster array, we can make it so it doesn't actually control our orientation at all. Even if two fail, we still have two in pairs. That's how they're fed. So yeah, bust dry. That is the mass of this. This is 20. It's less than that really. It's more like 21 kilograms. But I'm just adding a safety margin here. Bus terminal. So that is for our retrograde rockets. So that's if we are coming down to the end, and then we do a little burn right here. It's a propulsive way to slow down. It's not too different from Soyuz, right at the end, basically. Main chute mass, pretty simple. Because we also have a cutting option. Let's say there's an issue, or we just want to see what no mess of parachute looks like. So we can say we can cut it, and so that decreases our mass, of course. And so this crush device that I've talked about with this probe is a honeycomb pad. And that'll take a lot of our energy. And part of the computation is to know how massive it is, but it's also, more importantly, has a greater impact here. How much ablator? We use a Pika simulator. I'm thinking about actually moving over to a ceramic. It would be smaller and lighter. I don't think it would really matter. It won't change too much because we still don't really ablate anything. We're not heating up that much. It's the simple nature of having so much of it. It doesn't matter. Aeroshell mass. So that's how much the back end and the front end is. This is the heat shield more side. I mean, it technically is all of a heat shield. It's just our entry side is far more. And if you want to learn more about our aeroshell design, that's in the previous video. There should be a playlist. And then here's our prop. Propulsion to actually re-enter. So here, this is the terminal retrograde pack, which is the propulsive landing. And they're based on G12 motors. They have a decently long burn time and not like high peak thrust. So they're actually pretty reliable. I say that it's true just because I like seeing the printout that you'll see. I like the flag, basically, that says, hey, look, they deployed, even if we don't give them any fuel or have any amount of them. And we can also say at altitude or when the chute is full. It is more efficient to do it at altitude, and we have at 80 meters. We do have a downward facing radar for the probe. This is for multiple reasons, but mostly it's for deployment reasons. And then we have some geometry of our aeroshell, the area, the CD, and the probe area and CD. And then drogue settings, do we want to enable it? Do we want to cut it? Pretty simple. Main chute model, again, very simple. It's just saying this is our area. As you can see, I was testing out the previous version. And we currently deploy it at 10,000 meters. It's higher than you need, but it's it will give us enough height that it deploys at to give it more time to open. And then also some of our higher landing sites need that. So basically we've got some more parachute stuff, so the riser force, the reef. So basically, like we're saying, how long does it take? Here's the force, this is the stretch amount. And of course, cutaway, we don't cut away. We can also force it. We have that flag as well, basically saying, hey, if the riser force is, we're going too fast for the parachute to deploy, we're going to deploy it anyway because we don't have a choice. And then we have a survivability printout, and it's just basic, like, what can the probe handle? 300 G is about what we're expecting maximum for it to be able to fully function. It will function at a higher impact. And that is also our touchdown vertical velocity is also important. So here, please note, so this is for calculating how much energy the honeycomb structure will take. And you can just copy paste that from this bad boy. I don't remember exactly what it's called in this calc, but it's that. And then I'm not going to go into the functions because it's so much. So instead, we're going to just run the script and kind of just look at the analysis. There are bugs, shocker. Do not want to save, but I do want to show. Save also shows you the graphs. It's just what I don't care about right now. So, well, it's loading in. Yes, I know doing things outside of Python is more efficient. Guess what? I don't care. It runs real enough time to me. So as you can see, we have a few figures loaded up. So let's do the first. Altitude versus time. Okay. This is when our entry interface starts. Yeah, that makes sense. So we're slowing down. And then boom, this must be parachute. Beautiful. Terminal corridor. We've got our dynamic pressure, vertical velocity, and touchdown. Here it displays as linear because it is kind of linear. Hello. Speed versus time. Okay. So here's us in orbit. We've performed a burn, entering, boom, drogue, main chute deploy, cut drogue. Our velocity goes down quite a bit. Doesn't go to 0. Oh, vertical velocity. 0. Okay, that makes sense. We're in orbit. Re-entry interface. It's kind of funny because it always feels like these graphs are showing the same thing, which they fundamentally are. Okay. That's a... Oh, okay. I was like, that is a bug. No, that's when the main chute deploys. For main peak aerodynamic G's, totally fine on the probe there. Vertical G load, same thing, fundamentally. Heat flux, okay. So as you can see, our watts per area, so like, our actual heat, goes to about 6.5 at just after 200 seconds, which is about what I would expect for a Mars reentry. So we like to see that. Integrated load heat, so that is, it's just our cumulative, so anything that we're adding in this case, and obviously it's going to flat off after we slow down enough to deploy a parachute. So here we have our dynamic pressure. So this is Kind of, if you've ever watched a rocket launch, you've heard max Q, so that's the maximum aerodynamic pressure that the spacecraft, or the launch vehicle, sorry, experiences. And you can kind of do the exact same opposite for reentry, or EDL in this case. And as you can see, to jettison, we need to be below 300 pascals, and we never reach that, so totally fine by a factor of 2. Main chute riser, fine. Forces below 5,000 newtons, we are fine. Component temperatures, so as you can see, our heat shield. This is not the best calculation, I will admit. It's because we don't really deal with dissipating heat that much, which has its pros and cons. It doesn't look great here. It's easier to not have it dissipate properly. Chute inflation, looks like a straight line. It's not, trust me. Yeah. Sorry if I'm going through these pretty fast, but you can literally plug in my script and it'll show you the exact same thing. Vehicle mass, so it shows our initial. This assumes that during our burn, we do not change mass, which isn't true. That's a small tweak, and it's to the benefit of saying worst case. That's what I'm going with. Oh, here's our descent quarter. I really like this one. So this is saying our vertical velocity versus our altitude. So we're saying that we start at 0. So you've seen these graphs before. It's just presenting in a new way. And I really love to have these because it tells you a lot more. Because before we were like, it looks like that's the main chute, or this is the drogue and this is the main chute. Not quite true. So I really like to see this. But it looks like all of our settings are working. Dynamic pressure versus altitude. Again, we're fine. No worries on that. Mach versus altitude. Looks like we hit a peak Mach, well, in the atmosphere of about 14. But 8 is when it really matters. Okay, heat flux versus altitude, same thing. Basically just saying, hey, look, this is when it matters the most. So that's the largest. Our G loads. So these are our aerodynamic loads. Again, makes sense. This is including our parachute. And altitude versus downrange. So this is saying start of the sim, we are that much downrange. And the all-important printout. These are super data rich. I really, really like them. So we're saying, here's our orbit, and we calculate that we need 52 meters per second. And hey, look at that. We have enough. So, well, I guess there's another way to show it. So that means we need 4.5 kilograms, and we have 5, so we're fine. Main chute, so these are just printouts of times. Our heat loads, actual values, this is our peak load, looks like 11 Gs. That's fine. 1400 Pascal. Okay. And then, so this is for when we deploy our aeroshell, because we first deploy the top part and then the bottom part. And there's a couple of reasons for that. It's mostly reducing mass and things like that. Because if you deploy the bottom too fast, remember, this thing is light and has a really big CD and decent sized area. So it'll just go off and then smack back into the probe. So you have to be aware of that. So this is what we're saying. This is the time that the bus is exposed to the air. Staging snapshots, these are just for more computation checks. Final shoot, looks like we are good. Cutaway, false, blah, blah, blah. Okay. Final landing and impact. This is important. So what time do we land? What is our vertical velocity? Looks pretty good to me. Looks about 12 meters per second. That's undershoot. I'm not sure why it says this. That might be a bug. I am a believer of these values though. These are all matching because I have some check functions in here. So I'm not sure what's up with this. Okay, I'm dumb. It's just average. I have forgotten. There's a few lines of code and I wrote this a while ago. I'm sorry. Okay, so impact. So 2.3 kilojoules of energy is no joke. That's a lot of energy in an impact. And so here we have our plateau stresses, our energy capacity of the actual honeycomb, and absorbed all. Looks like no, it didn't. That's okay. So it looks like we have impact of 141 G, which is quite a bit. But again, probe is designed to be fully functional at 300, so it's fine. And we can change the modes of the honeycomb. That's kind of like for tweaking. Obviously, I'm not tweaking this anymore. And then when you run this code, this, I would argue, is the most important part. It's just saying, hey, does it hit our limits? Will it survive? Hey, look, passes, because it does. And then if it doesn't, it'll give a tag and a little bit more information. Our G-load summary and our phase durations. So entry interface to jettison is 26% of our time, and then jettison to main shoot is 82. And then another event timeline, and then we are our outputs. So that is the EDL script. Thank you very much for watching. Have a wonderful day. Bye-bye.